Good afternoon to all the attendees. Thank you, Professor Du. Thank you, Professor Louis, the entire Lanzhou University of Technology. Professor Han, thank you for your presentation. It's a great pleasure for me to give this presentation to your students and your guests. Well, you remember, I have been in China several times. Among these in 2009, in Lanzhou University of Technologies, in conjunction with the Assisi conference in Guangzhou. I would like to send my hello to Professor Fulin Zhou, Professor Ping Tang. I know maybe they are listening to me this afternoon. And in 2017 and 2019, I have been in Shanghai at Tongji University, invited by Professor Tang and Professor Inzhou, respectively. Thank you to all of you. Well, today I'm going to present an updated state of the art of seismic isolation in Italy with the recent application and also experimental experiences during the recent earthquake. My presentation is organized in, as you can see from this summary, but let me start with a very general introduction of seismic isolation. This is very useful for your students, mainly. It is based on the analysis of the elastic response spectrum in terms of acceleration. This spectrum gives the maximum acceleration in a structure as a function of its fundamental period of vibration. The acceleration spectrum, the blue line in this slide, starts from the peak downward acceleration, which is the value for a period equal 0, and presents maximum amplification in a range of the period up to 1 second or more. Unfortunately, most of our civil structures have a fundamental period in this range, exactly in this range. Seismic isolation increases the fundamental period of vibration, usually more than 2 seconds, so that acceleration can be reduced significantly. This reduction is offset in terms of displacement. Displacement increase with the period of vibration, red line in this diagram, but these displacements can be concentrated at the base of the building, while the superstructures behaves almost like a rigid body. In such a way, we realize the so-called decoupling of motion between the motion of the structure and the motion of the soil, and it is possible designing in the elastic range. In other words, to obtain what I call a zero earthquake damage building. New idea, ingenious idea? Well, ingenious maybe, but not new. The ancient Greeks used the foundation composed by a continuous stone plate separated from the ground by means of a layer of clay mixed with charcoal and ashes, and also other techniques. A similar solution was proposed in 1909 by Calantrientes. He used a layer of talcum powder between the foundation and the structure. But the first engineering device was developed by Stevenson in USA in 1868. He called it a seismic joint. This consisted in spherical rollers in niches and was used to protect the lighting system in Japan. Well, actually, two events were very important in the development of seismic isolation. The first was in the 70s of the last century, when the Malaysian Rubber Producers Research Association produced in England the first steel elastomeric devices based on the vulcanization process. So we started the first application in the USA, in New Zealand, and mainly in Japan. The second event was the construction of a nuclear power plant at Croix in France with seismic isolation. In this case, seismic isolation allowed using the same project already used for other installation in site with peak ground acceleration equal to 0.2 G, whereas at Croix it was 0.3 G. Well, the physical and the mathematical principle of seismic isolation can be easily understood with a single degree of freedom, such as the portal in this slide. I hope you can see the entire screen, or not?
Yes, yeah, we can see the screen.
Okay, maybe it's better like this. Okay. So this is the mathematical principle, which is the basic of seismic isolation. We insert isolation under the column of this portal and added a rigid beam between the column. So we obtain a 2-degree of freedom system. The equilibrium equation can be easily written assuming as a Lagrangian coordinates the absolute horizontal displacement of the floors, so the modal shapes can be found, and the frequency, of course. The first involves usually only or mainly the isolation system, the second also the portal. We write the equilibrium equation in the modal shape in terms of principal coordinate, and in the modal space in terms of principal coordinates, and consider the participant factors. In order to have the participant factor of the second mode very low, the parameter epsilon should be small enough. It is given by the squared ratio between the fundamental period of the structures as fixed base and the fundamental period of the isolation system. So we conclude that the fundamental period of the isolated structure must be much higher, at least 3 times, than the fundamental period of the fixed base structure. It's blocked, sorry. Okay. Seismic isolation is not the medicine useful for all the diseases, but there are some conditions to be respected. The superstructure must be rigid enough to guarantee the coupling of motion. For the same reason, seismic isolation is not recommended in presence of soft soil, and it requires seismic joints between the building and the adjacent structure. Alternative solution can be the energy dissipation systems. Well, more information about the history and the basics of seismic isolation can be found in this paper. I send to Professor Du all the paper I'm going to cite in this presentation. Well, let's go to the second step. Let's have a look at the most used devices. It is important to remind, first of all, that the isolation devices have mainly a supporting function. They bear vertical loads in operating condition and under seismic condition also, of course. But they have a horizontal stiffness, a low horizontal stiffness to allow the relative displacement during seismic action, an adequate stiffness against low horizontal forces such as wind and traffic, and a good capability of dissipation, recentering, and lateral constraint under service horizontal loads. This last function can be also entrusted to auxiliary devices. These are the most common isolation devices. We have rubber bearings, top left, plane sliding devices, bottom left, curved surface slider, top right, and linear recirculating guides. This last type of isolators is mainly used in Japan, not so much in Italy, probably due to its cost. Let's start from the elastomeric bearings. They have cylindrical shape with external diameter d. They are made of N horizontal rubber layers, steel laminates of diameter a little smaller than d, and 2 steel plates of bigger thickness at the top and at the bottom. This is the vulcanized portion. hot vulcanized portion. Then we have two steel plates, upper and lower, each with at least 4 anchors for the superstructure and the substructure. We define the first shape factor, S1, which is related to local instability, and the second shape factor related to global instability. The devices are characterized by a low horizontal stiffness and a vertical stiffness, defined usually as in theory of elasticity, of course. Very important is the ratio between the vertical and horizontal stiffness. We do not use usually isolation in vertical direction, only in horizontal direction, usually. Each layer of rubber is subjected to shear, compression, and bending. This causes angular deformation. Due to shear deformation, the effective area under vertical load is reduced, and codes usually require the following checks about the strain due to shear only, about the total strain, the stability check, and the check of stress in steel laminates. The behavior of elastomeric device is characterized by force displacement curve. For each cycle, we have 2 parameters: the equivalent stiffness, which is given by the ratio between the maximum force and the maximum displacement reached in each cycle, and the equivalent viscous damping coefficient, which is a function of the area contained in the cycle. Usually these parameters in the design, linear design, are defined with the reference to the design displacement, maximum design displacement. The equivalent viscous damping can be increased up to 25–30% by inserting 1 or more lead cores within rubber bearings. The advantage is that we can use low damping natural rubber, which is more resistant to failure. The disadvantages are that the manufacturing process is more difficult, and the recentering capability is lower due to the lead, of course. Then we have sliding devices, usually made of steel and TTFE materials with low friction thanks to lubrication. Their load carrying capacity is independent of the displacement. They have no recentering capability. They cannot be used alone. They can be used in conjunction with elastomeric devices or auxiliary devices. And finally, we have the curved surface sliders. They have, without the contribution of other elements, the recentering function and the dissipation function. Friction pendulum system was first developed in the USA, then also in Europe, first in Germany, and finally also recently in Italy. We have single curved surface slider on the left and double curved surface slider. In this second case, we can have larger displacement with the same size of the devices, but the friction could be different for the different surfaces. So sliding on one surface is first started, then also the other. Nowadays, we also have double curved surface slider, which the internal element is not articulated. I don't like this kind of pendulum, and also triple curved surface slider, in which the problem of different friction is much more important. How it works? Well, the principle is the same of a simple pendulum. We write the equilibrium between the internal forces and the weight component, and deduce that the stiffness depends on the mass. As a result, the period of vibration is independent of the mass. The actual behavior is more complex, as you can see from the diagram in the bottom of this slide. We have 3 kinds of friction: the static friction at the onset of motion, the dynamic friction during the motion, and the static friction at the change of velocity sign. For technical application, we use a simplified bilinear system model. The stiffness equivalent is defined at the second stiffness. Damping is related to the dynamic friction and to the radius of curvature. And also the period, it depends on the radius and also on the displacement. So we have a strongly nonlinear behavior for this kind of device. Static friction should be high enough to guarantee a good stiffness with respect to static loads and low seismic event, but it is a problem of this type of devices. I'll tell you something more later. Several models have been proposed for curved surface slider. I like very much the model proposed by several authors. Among these, Lomiento and Benzoni, my friend that lives in California now, and are also Assisi members. I prefer this model because it allows accounting for the static friction directly. The friction coefficient mu is given by the product of two functions. One is a function of the axial load n and the velocity v, and the other is a function of the heat generated at the lying surface because of the energy dissipation. All the constants present in these formulas must be determined experimentally. In the first diagram on the left, the friction coefficient is plotted versus the axial load for three values of sliding velocity. Zero velocity means static friction. Low velocity corresponds to the minimum value for friction coefficient. High velocity corresponds to the maximum value for the dynamic friction coefficient. In the same diagram, you have also the friction force plotted for the same three values of the sliding velocity and the dotted line. As you can see, the friction coefficient reduces with n. The friction force, of course, gets higher with n. In the second diagrams, you can see the friction coefficient versus the sliding velocity for three values of the vertical load. Well, how can we combine the different devices? We can use elastomeric devices alone with the sliding devices. Sliding devices cannot be used alone, but with the elastomeric devices and or auxiliary devices. Curved surface slider can be used alone with auxiliary devices. Let's go to the third step. And how can we perform the preliminary design of a seismic isolation system? We realize an isolation interface between the superstructure, which is to be protected, and the substructure, which includes the foundation. We realize a full isolation if the superstructure remains within the elastic range in the design seismic condition. Otherwise, we have wholly a partial isolation. Full isolation allows us to realize a zero earthquake damage building. Partial isolation is not a good solution because if a superstructure will damage, its period of radiation gets higher and could be closer to the isolation period. Where should the isolators be placed? Well, it is not necessary to be all on the same horizontal layer, but each of them must be placed horizontally. Structural element between isolator and the supporting deck must be very rigid in comparison with the isolators themselves. The isolation interface is a sort of a continuous surface which passes through all the isolators without intersecting neither the superstructure nor the substructure. Inspection and replacement should be guaranteed for all the devices. Gaps necessary between the superstructure and the ground should be guaranteed. What about the elevation? Well, we prefer to put the isolator at the lowest story, the basement of the ground floor mainly, So we isolate the entire building, and we can put them at any intermediate height of the chosen story, but it is better at the top, because if the isolator are at the bottom, you can see in the figure on the right of this slide, this column or wall will not shake together with the lower floor. So a gap should be designed to absorb this relative displacement. Well, what about the deployment in plan? For reinforced concrete building is very easy, one isolator under each column. For masonry building, mainly at the crossing of the walls. Well, furthermore, we have to optimize the dynamic behavior of the building, obtaining that the first two modes are translational only. This is certainly verified if the projection of the center of mass is very close to the center of stiffness of the isolator system. If you use elastomeric and sliding devices, the elastomeric ones should be mainly along the perimeter, and in order to have a suitable torsion stiffness. The number should be at least 4. I suggest at least 8, because redundancy is very important in isolation, in seismic isolation. If we use curved surface slider, the coincidence between the two centers is automatic in theory, because the stiffness is proportional to the mass, as already said. But due to the variability of the friction with the axial force, this is only in theory. This is not true in practice. It is very important, the definition of the design earthquake, and in this case, European code and Italian code are quite different. In both cases, we use the earthquake that have a probability of accidents of 10% in 50 years, and in both cases, we use a higher safety level for the isolation devices. But according to the Eurocode EC8, we account for the importance of a structure by amplifying the elastic spectrum by an important factor, 1.2 for relevant and 1.5 for strategic structures. Then we multiply the design displacement by 1.2 for the check of the isolator. According to the Italian code, we account for the importance of a structure by reducing the probability of accidents of the design earthquake, so considering higher seismic acceleration. And the same we do for the check of the isolators. The modeling of superstructure and substructures is very easy because they are linear elastic system, at least in the full isolation. The isolation system can be modeled as a linear system and also as a nonlinear system. To have no vertical amplification, vertical isolation, the vertical stiffness of the isolation system must be at least 800 times the horizontal stiffness. It is also important to fix some consideration about the load combination. Because under static load, we have self-weight G1, other permanent load G2, and variable load QK. And all of them are amplified by means of a load factor gamma, 1.3, 1.5. Instead, in the seismic combination, loads are not amplified. And the only safety factor is related to the reduction of the strain material in the ultimate limit state, of course. Another important thing is the importance of the vertical component. It should be always considered because a vertical acceleration can reduce the vertical load on a masonry wall or a concrete column, it's the same, and so reduce its shear resistance. How we fix the isolation period? Well, we choose the spectral amplitude SE star by means of architectural consideration and economic evaluation, and find the corresponding isolation period using the acceleration spectrum of the superstructure. This is a good isolation period only if guarantees a suitable decoupling and also an allowable displacement. For the preliminary design, we can use a very simple model of rigid body on elastic horizontal springs. It's a 3-degree of freedom system, 2 translational and 1 rotational. And suppose that the first 2 modes are translational only into the main direction. From the period, we can deduce the stiffness, total stiffness of the isolation system by this very simple formula, and then the stiffness of the single devices once n has been established. For curved surface slider, we use this formula and we deduce the radius from the period, but in this case also the friction factor and displacement are included. So usually this can be done by means of iterative procedure. The preliminary design can be completed evaluating displacement in each devices, but these rules are quite different from one code to another. I just remind that you can add the displacement due to the accidental eccentricity and combine the earthquake in one direction with the earthquake in the orthogonal direction, usually. These are typical seismic joints. It's not difficult to realize them. And these are typical flexible pipes for both residential and building and also strategic buildings. Other details on this subject can be found in this paper, and about curved surface slider also in this one, but we're publishing more recent, more up-to-date consideration about that in the next future. So let's go to application of seismic isolation in Italy. And the first modern application in Italy dates 1976 and concerns the Somplago Viaduct in northern East Italy. Thanks to the seismic isolation system, which comprised sliding devices on the pier and the rubber bumpers between the deck and the abutment, as you can see from these pictures, the Somplago Viaduct survived the Friuli earthquake in 1967. It was just completed. And the first application in buildings dates 1981 and concerned a fire command building in Naples. It is a steel structure suspended from the top, from a top reticular beam, supported by reinforced concrete tower to have lots of free space on the ground floor for the works of the fire command, of course. In 1990, the Telecom Italia Center in Ancona was completed. In this case, impressive on-site release tests were performed on one of the 5 buildings with an initial displacement of 11 centimeters. An increase in the use of seismic isolation in Italy happened after the Molise earthquake in 2002 and the L'Aquila earthquake in 2009. Among the most interesting application, it's worth reminding the new school at San Giuliano di Puglia in Molise, which was the first school in Italy to be designed with base isolation. It is composed by 2 buildings rising up from a single base deck, a very small artificial ground. Another building, very nice building, was this Civil Protection Center at Foligno. It has an hemispherical shape, and it's supported only by means of 10 elastomeric isolators along the perimeter. We'll go back to this building later, speaking of seismic monitoring, because both the San Giuliano School and this building are monitored by means of an accelerometric network realized in the framework of a project organized by ENEA. The use of seismic isolation increased rapidly after L'Aquila earthquake, thanks to the buildings for temporarily hosting the homeless residents when these were realized in L'Aquila, and consisted in prefabricated houses made of reinforced concrete, steel, or wood. They were placed on an isolated reinforced concrete slab, and the slab was supported, as you can see from this slide, by 40 curved surface slider installed at the top of a circular column rising up from a foundation plate. This is the tallest building in Italy, just 8 floors in Messina, tallest isolated building. While in this building in Rome, seismic isolation is used to realize a chinned mass damper at the top. Well, most of the application in Italy are for the retrofit of existing building. In this case, a new sub-foundation was realized, and we can see the main steps of the work from this slide. The existing foundation was composed of plinths and 2 piles, as you can see from the left top. Each existing plinth was reinforced. A new large column with a new plinth was realized under the existing one, and then the isolator device was inserted between the old plinth and the new column, and it was put in action using flat jacks injected with epoxy resin. The 2 existing piles were finally cut, separating definitely the old and the new plinths, as you can see from the last picture on the right bottom. In this other case, instead, the devices were inserted by cutting the columns. The column was first enlarged in the lower portion, as you can see from the left top picture. Then metal brackets were used and hydraulic jacks were put between them to unload the portion of the column to be removed. And the segment of the column was cut by means of a diamond wire. And finally, the isolator was inserted in the column. This is a very interesting technique that allows the lifting of the building. And this is realized by Soles, which is a company in the northern Italy. On the left, you can see the existing building, 1.1. 2, we realize a first foundation plate not linked to the building and supported by new piles on purpose built. And 3, a second foundation is realized. This time, this is linked to the structure. The 4th point, we position hydraulic jacks between the 2 foundations, and we can lift the building, of course. Then we insert 0.5, the isolator between the 2 foundations, and finally we take off the jacks, and the work is completed. And very recent application regards cultural heritage in L'Aquila. This is a very nice house, and in this case, 2 new foundations were realized. The upper one is a continuous concrete beam, and it is linked to the masonry walls, the upper masonry walls. The lower foundation is composed by plinths which were successively connected by means of a reinforced concrete plate, of course, and the isolation devices were placed between the first and the second foundation. Obviously, these are the construction phases. The work were done acting on small portion, one at a time, of course, and this is a picture which gives an idea of the final situation after the work. You can see the continuous beam, concrete beam, the plinths, and the isolators between them. This system allow the application of the isolation system under the foundation in the ground without touching the structure. Therefore, this is a suitable solution, especially for cultural heritage building. It can be applied also to entire aggregates or historical center, because the pipes are introduced by means of pipe jacking, of micro-tunneling, and the isolator are put just in the middle of the horizontal pipes. A similar solution has been proposed for new buildings, and in this case we have a sort of artificial ground above which we can build as it was, because this is often required in the reconstruction of historical centers in Italy, especially in the central Italy after the seismic sequence that started on August 2016. Recent application, recent state of the art in Italy can be found in this paper published last year in the Soil Dynamics and Earthquake Engineering journal. So go to the last step of my presentation. This is about seismic response to real earthquake in Italy, response of isolated building. Actually, seismically isolated building behaved very well, also under strong events in Japan, USA, New Zealand, and also in China. But what happens in case of low energy earthquakes? Well, in Italy, we tested this last situation, and we first consider that this building, I've already introduced this building previously, and it was the operative center at Foligno. It has been instrumented by means of 12 accelerometer. 1, 2, 3 are at the basement, as you can see. From 4 to 10 are at the first floor, just above the isolation devices, and 11 and 12 are at the top of the building. This is still the isolator deployments and a plan view of the isolator deployments. All the events of the seismic sequence that struck central Italy starting from August 24th, 2016 were recorded. Those with the magnitude higher than 4 are reported in this map on the left, yellow circle, but some of them had magnitude higher than 5, up to 6.5. They are reported by means of a red star. In the diagram on the right, you can see the magnitude of each event plotted versus the epicenter distance from this site, which is on the top left of the map reported on the left side of this slide. The amplitude of the circle is proportional to the energy at the foundation, which has been measured, which has been estimated by means of the area's intensity at the foundation of our building. We analyzed the result of just one event, and this is the strongest event recorded on October the 30th, 2016, and we have the recordings at the basement with the green boundary, and then we have the recorded just above the isolation system, blue boundary, and then at the top of the building. You can see that there is no amplification from the basement to the top, but you can also see a change of the frequency content. And this is confirmed by the Fourier spectrum of the recordings. You can see a first resonance frequency at around 1 Hz in both directions, and these are certainly associated to the isolation system. But the isolation frequency in design phase was 0.38. So we have a much higher frequency during the earthquake, this low energy earthquake. Higher frequency content in these diagrams are due to the superstructure, of course. Where from wavelet transform, we can see that the frequency, the resonance frequencies change also during the same earthquake. I'm not going in detail about this diagram, and but you can see that from these diagrams that the frequency, the first frequency, changed also mainly from one earthquake to another. This means that we had a very important non-linear behavior of the isolation system. The lesson from this experience is that the resonance frequency could increase too much and be very close to the resonance frequency of the superstructure. And this should be taken into account when designing an isolation system made of elastomeric isolators. Detailed analysis of this isolation system is contained in this paper published last year on soil dynamics and in soil dynamics and earthquake engineering journal. I'll give you this paper, of course, through Professor Doom. Well, the last example is that of one of the building of L'Aquila after L'Aquila earthquake, and it was isolated by means of curved surface slider, and the earthquake is the same of the previous example, and in this case, going from the bottom to the top, an amplification is very apparent. So the isolation system did work properly. As you can see from the Fourier spectrum, we have no amplification at the low frequency, but we can just see very well the frequency, resonance frequency of the superstructure. And also the analysis of in terms of relative displacement between the first floor just above the isolation system and the foundation below the isolation system, you can see that relative displacement were very low and probably also related to the deformation of the column and not to the sliding of the devices. Why this behavior? Yes, because it is related to design choice, because they decided the friction using the ultimate vertical load, for example, 3%, the friction coefficient. But during the earthquake, the vertical load was much smaller than the ultimate vertical load, maybe 1/3, 1/2 of the design ultimate vertical load. And so the friction coefficient was much higher. And in fact, if we go back to the previous slide, you can see that we have peaks of about 1.2 G at the top of this building. Not only, but the static friction coefficient can be much higher when the isolator are not working for a long time. What is the lesson from this last example? The onset of motion should be analyzed carefully. We're doing that. We're publishing papers about that in the next future. And the seismic isolation of the superstructure could be much higher than that assumed in the design. More detail about this example can be found in this book chapter published last year. This is my last slide. Thank you for your kind attention. I hope it is enough for you. And thank you very much for your kind attention.